said upper and lower sums, it meant something different than I thought it did.
Oh, no,
So,
were you gonna explain it? Should I just want you to?
no, it's, yeah, like part of that's my fault for doing a bad job.
Oh, yeah.
All right. So we'll start with some questions. We're going to start with number 7 here. I'm going to draw the graph of this function so I can like do a picture to help us understand like what's going on and what the vocabulary is saying. So this was y equals, where was it? 2 plus sine x. Oops. And we want grid range 0 to pi, and we just want to go from 0 to 3 should be enough. Okay, so this is my picture. I'm going to just grab that and drop it into here, and then try to make it like a respectable size. Okay. So I want to talk about what the book means by upper and lower sums. So if I'm doing this from n equals 2, so we have 0, we have pi, and then like pi over 2 would be my second interval, right? So when it says lower, what it's talking about is I want the minimum y value from this first interval. That happens here, right? So that would be my first lower rectangle.
Wait, so why did you do that again? Like, is it because it's the lower?
Because that was, if I look at the curve on that interval, it's the lowest value on the curve, right? Now I'm going to look at this subinterval. I'm going to find the lowest value on the curve from like there to there. So that's this value. And I'll draw my second rectangle. So what I have is this distance, which is pi over 2, times this height, which is 2. And then the same thing for the other spot, right? I'll just call that L2 for lower 2 or low 2. So what do we get here? We get 2 pi, right? If I do an upper now, I'm just going to take the highest point on that first interval, which is up here. So that's my first rectangle, which is pi over 2 times 3. And again, the second interval, that distance is still pi over 2. This is still the highest point on my second subinterval. So I have 3 times pi over 2, which gives me 3 pi. So I know the area under the curve has to be somewhere between 2 pi and 3 pi, because the first one is guaranteed to be an underestimate, because I'm taking the lowest y-coordinate on every subinterval I choose. And I know that the upper has to be an overestimate, because I'm taking the biggest y value on every subinterval I choose. So I'm guaranteed to have an upper and lower estimate. If we did left hand and right hand rules here, we got to have gotten the same answer for each. And it's not the answer for the problem. So that's why it's asking for an upper and lower. We didn't talk about what upper and lower meant. My fault for not doing that and or assigning this particular problem. Chanel.
So why would you run into an issue with, I know you'd get the same answer, but how would you get the same answer if you were to do
Okay, so if I let's grab, we'll do the left bound or the left want rule in green. Okay. Is that okay? And then I'll do the right rule now in red.
Oh yeah. Oh yeah. I get it.
So I got the same answer for each one, right? And that's not the answer to the problem. That's not actually the area under that curve. So the left one, the left rule I did in green, the right rule I did in red, you can see that it's going to be the same sum, right? Yeah. I should say correct, since I'm using left and right to mean the direction. I should say that's left, right? It's confusing for everybody. My apologies. So that's the idea for that problem. So again, if you can do it for 2 subdivisions, you can do it for 4 or 6 or whatever the question asks for after that. But that's the idea. And again, if it helps you to draw the picture and like draw in your rectangle so you can really kind of physically see what it is you're doing, do that. Keep in mind that this value here is like, if that's my function, that was like f of 0. And this value would have been like f of pi, right? This value would have been like f of pi over 2. And this value is also f of pi over 2, right? Like that's just the height of your rectangle. It's the value of the function evaluated at some point on that subinterval. The way we chose the point on the subinterval was so that we had the maximum or minimum y value. Chanel, does that feel better about 7 as what's going on?
Can you do n equal 4? Because I was confused with the report. I'm so sorry.
It's okay. So if I do that, I just have pi over 4 and then 3 pi over 4, right? So, hi, Mr. Sharp.
I don't think she said B11, but that's you.
Yeah, I'm not going anywhere. Probably Kroll is across the hall. Yeah, probably just goofed the. No problem. Okay, so let's do the lower, right? And if I do the lower, the upper should be fine. So the width of my rectangle is pi over 4, right? So if I look here from pi over 2 to pi over 4, the lower value is at pi over, or is at 0, right? So that's going to be f of 0, or you could write just 2 there, right? Because we can read from the graph. On the next interval, from pi over 4 to pi over 2, again, that width is pi over 4, and we're looking for the lowest value on that interval, which looks like f of pi over 4, which is, I don't know, 2.6-ish. The next interval, the width is still pi over 4. And if I look here, the lowest value on that subinterval is at 3 pi over 4. And again, that value looks to be about 2.6-ish. And then if I look at the last subinterval, that goes, again, the width is pi over 4. And the value there looks like to be at pi is the lowest spot, which looks like 2. And there we go. That's it. Now you grind it out in your calculator and you're done.
Okay. So is this kind of unique process? Is this just unique to the question because of the
Yes, because
rectangle situation?
Because it's asking for an upper and lower
estimate?
Yes.
Okay.
And
so,
because this is, and the reason that it's going to be an issue is because notice this function is increasing and then changes to decreasing, and it's symmetric.
Okay.
So you're going to get the same left and right values almost inherently, unless you do something weird like do n equals 3.
Okay.
Right? And I think there you might not get the exact same answers, but it's just a product of this particular.
Okay. Thank
Yes. Pierce. 2. Sure. 2 part A, even better. Because once you can do part A, you should be able to do the rest of it, right? Okay. Okay. And I'm probably just going to do one of
That's fine, yeah.
the part A.
Yeah, I just want to make sure.
Okay. So we go from 0 to 12, and we're using 6 subdivisions. I can see that because it says L sub 6. So 12 minus 0 divided by 6 is 2. So I'm just going to kind of do this for myself to show myself where those subdivisions are. So this is like 0 to 2, that's like 2 to 4, it's 4 to 6, 6 to 8, 8 to 10, and then 10 to 12. So if I'm using left endpoints, so the first subdivision from 0 to 2, I'm going to use the left end of that. That's my first rectangle. So that looks like that's going to be 2 times 9. And then from 2 to 4, I'm going to use the left end of that. So that looks like it's going to be 2 times maybe like 8.7 or something. And then the next one, I'm going to use the left end of that, which is going to be 2 times maybe 8.2 or something. And then again, I'm using the left end. So that looks like it's going to be like 7.2. The next one is here. That looks like it's going to be like 5.8 or something. And then my last subinterval looks like that's the left end. That was 5, 4, 3. So like, oh yeah, like 3.8. Something like that. So then I just add that stuff up. Does that feel okay, Pierce?
Yes.
And that's the gist of it. Like I'm literally just using the graph to find the y value. I'm just drawing the Riemann sum.
Okay. All right, thanks.
Yep. And this would be a good one to even like, if you're going to do it in OneNote so you can like just steal the picture and draw your Riemann sum each time so it's easy for you to see what's going on. But like the picture really helps, right? If I'm just adding up the area for those rectangles, like if I can draw the rectangles, no problem, right? No one.
For that, just estimate the height.
Yeah, because it says find estimates.
Yeah.
So like it doesn't give you what the function is. There's no way to tell what the heights actually are. I'm just guessing from the picture, and I might have like read the y value wrong even in a case where maybe it's supposed to be like 6.8 or 5.8 or something. Like I don't know. I just was like trying to do it quick because you got the idea pretty quick, I think. Yeah, no problem. Okay, so let's start 5.2. So we're on in 5.1, we gave the idea that somehow this process of anti-differentiation that we looked at in 4.9 is related to the area under a curve. In 5.1, we developed a way to calculate the area under that curve by taking the limit as n goes, or the limit, or ending up an infinite number of rectangles underneath the curve, right? That are like, whose widths are now getting infinitely small. So in 5.2, we're going to start with the definition. And what we're going to say is that infinite sum of rectangles that we saw in 5.1, we're going to call that the integral, and we're going to denote it with this notation. So that reads the integral from a to b of f of x dx, which means the same thing as that sum of infinite rectangles that we saw was the same as the area of the curve. So this is equal to the area. that we saw in 5.1. Okay? Does everybody feel okay with this? So we say, as long as this limit exists, we'd say that f of x is integrable, is the term we use, just like we talk about if the derivative exists, then it's differentiable. Everybody's okay with that notation, the language? Yeah. Okay. So let's talk a little bit about that integral notation. So this symbol here kind of looks like a stretched out letter S. Everybody kind of see that? Why do you suppose we choose the letter S? S for sum, because really what an integral is, it's the sum of an infinite number of rectangles. That symbol is called the integral sign, just like d dx is your derivative sign. The a and the b, the a we would call the lower bound, the b we call the upper bound, or the upper limit and the lower limit, excuse me. F of x we call the integrand, that's the function that we're integrating. The dx for right now is just kind of like tells us where the integration stops, right? So the start is that integral symbol, the end is where we see the dx. We'll talk more about like what the dx kind of means theoretically and conceptually a little bit later, but for right now you can think about it as like integral symbol start integration, dx is where we end integrating stuff. And that process of calculating the area then is called integration, right? Is everybody okay with that vocabulary? At least for now. Again, if I use it and you're not familiar, you don't remember what it was, just stop and ask and we can talk about it again. I'll remind you all. No problem. So notice that this definite integral is just a number, right? It's the area under a curve. It's not a function in terms of a variable. It's literally just a number. So the name of our variable does not matter, whether we call it the integral from a to b of f of x dx, or the integral from a to b of f of u du, or the integral from a to b of f of t dt. It doesn't matter, they all mean the same thing. The name of the variable is just a name. It's fine, whatever. Gives you the same answer. Is everybody okay with that? Okay. So this sum of rectangles that we looked at in 5.1, we're now going to give a name to this. We're going to call this a Riemann sum. That's a name you should know. The AP will use that vocabulary. They'll like ask you to calculate the Riemann sum for this, for this function using left-hand endpoints and like 10 subintervals or something. Everybody's okay with that idea? So just Riemann sum is just one of these adding up rectangles, just like we did in 5.1. We're going to be doing it again here in 5.2. Bernard Riemann is a German mathematician that's did a lot of very important things. What's up? No, this is just that's just adding up the rectangles. If it's again, doesn't need to be an infinite number of rectangles. It can be a finite number of rectangles. Yes.
So the xi, I don't know, is that an xl and xi in the parentheses?
That's an xi star.
Oh, okay, xi star is just like I'm sorry.
It's just some x value on the ith subinterval.
Got it.
So like if we start at x0 and we go to xn, we're going to have a subinterval from x0 to x1. So if I said x1 star, it's some point between x0 and x1. It doesn't matter what the point is.
So what does I equal 1 set again?
Just the first subinterval. Just something in here. Okay? Something between those two values. So if it was like 0 to 1, xi or x1 star could be 0, it could be 1, it could be 0.5, it could be 0.75, it could be 1.3267, it could be the square root of 2 over 2. Doesn't matter. Brady.
So the star comes from the last class you were talking about how we don't use the left or right order?
Correct. We don't have to do that. Although in practice, that's what we do.
Yeah.
But we don't need to.
Okay.
Because what's happening is that width of our interval is getting infinitely small. So like where you choose from doesn't end up mattering because it all kind of is flat anyways if you pick it infinitely small. Yes.
And then with the star, is it always going to be like a closed circle?
They're always closed brackets.
Okay.
Because you can pick a left end or right end.
Okay.
Those need to be closed, yes. Okay. So here is a Riemann sum. We're adding up rectangles. Here is our integral. That's the actual finite area between the curve. Or area under the curve, I should say. That's all I'm trying to show with this picture, is the difference between an integral and a Riemann sum. Riemann sum is rectangles. Integral is the actual area under the curve. Now, if we take infinitely many rectangles, we get the area under the curve, but we don't need to do infinitely many, and it's still a Riemann sum. Everybody's okay? Again, just some like concept and vocabulary. We haven't done any computation or any like grind here. We're just kind of talking about what this stuff means and how to think about it, right? One thing that we need to keep in mind with these Riemann sums is we're going to allow for rectangles to have positive area and negative area. So for example, if my curve goes below the x-axis, the Riemann sum rectangles that are below the x-axis are going to have negative area associated with them. So like if I look at this picture, notice the curve goes above the x-axis and below the x-axis. The rectangles that are below the x-axis have negative area. The rectangles above the x-axis have positive area. How do I calculate the area under the curve? I just add up the positive and negative parts respectively, and it's like a net area. So can areas under the curve be positive? Yes. Can they be negative? Yes. Could they be 0? Yes. Okay, so your integral values can be positive, can be negative, can be 0. That's all fine. Doesn't mean you've done anything wrong. Does everybody feel good on that? Okay. All right. So at the start of class, we defined a function as being integrable if the integral exists. Here's a theorem that kind of dictates when that's going to happen. So we say if f is continuous on AB, or if it has only a finite number of jump discontinuities on AB, then f is integrable on AB. That is, that our definite integral exists. Have you guys seen a function that has an infinite number of just jump discontinuities on a closed interval? No, you have not. You will in the homework. So on 69 or 70, I can't remember. I signed one of these two. It'll give you an example of this. The idea is just like recognizing that, hey, this function has an infinite number of jump discontinuities, so it's not integrable. That's the trick to doing it. I'm going to tell you right now. But you haven't actually seen a function like that. Like none of the things we use regularly have an infinite number of them. Now you could have like a step function where it's like, you know, does like one of these things. Right? And if you go from like 0 to positive infinity, that has an infinite number of jump discontinuities, but it's not a closed interval, right? So you've seen some stuff that has an infinite number of jump discontinuities, but the closed interval part is the part that matters, right? We haven't ever seen that. And we'll talk about in 69 and 70, I can't remember which one it was that I assigned. You'll see an example of a function where that's the case. And that's the thing to recognize. Okay. So if f is integrable on AB, definition 2 exists and give the same value no matter how we choose our sample points, our xi stars. So in practice, we just assume them to be right-hand endpoints. So the xi star just becomes xi. So this is the same formula that you saw before. We've just dropped the star. So delta x now specifically means this, and xi specifically means that. These are the exact same formulas that we had in 5.1. Okay? So this is the same definition as definition 2 that we led with, except now we said, okay, we can pick any sample point we want. Let's just always pick the right endpoint, and then it simplifies to this, which is fine. Great. We can handle that. I like being consistent and just doing the same thing every time. So, first example problem. This is an infinite sum of rectangles. It wants us to rewrite this as an integral. So, remember here that we have the integral from a to b of f of x dx equals the limit as n approaches infinity of the sum from I equals 1 to n of f of xi delta x. Right? We have this here, and what we want is to get that. Is everybody okay with what the question is asking for? All right. So my first order of business is I'm going to figure out what my a and b are for my integral. What are the a and b for this integral got to be? 0 and pi. Because that's the interval that we're finding the area under the curve for. And now I need my f of x dx. So what does my f of x have to be? Good. And notice that Braden dropped the subscript of I on there. You must do that. And we're done. That's it.
Why did the subscript again?
Because the I is part of the summation notation, right? Like you're taking an infinite number of rectangles whose width is this and the height is that, where the xi is changing for each segment of the sum. You're doing x1, and then you're doing x2, and then you're doing x3. Those are different x values. When you're integrating, there's no rectangles anymore, right? It's just the function. That's it.
So what was the difference between, what did you do to get that?
Almost nothing. Almost nothing. I just plugged in the a and b from here, and then I recognize the function there and turn delta x into dx.
Is that usually on 12 times?
Yeah, that's like it. It's like it's not more complicated than that. Brady.
For the summation,
Yeah.
Will I be equal to 1 or underneath?
Yes. Yes, because if you're adding up an infinite, I don't know why you would, I mean, I guess it doesn't have to, but like, why wouldn't it? In practice, for what we're going to see, yes, it would always be 1. Because you're just adding up an infinite number of rectangles. Why would you skip the first subinterval, right? Like that's saying like, oh, if we're starting I equals 2, then we're skipping the first subinterval. It's like, why would you skip the first subinterval? Why not then just change the bounds of integration so you start at where you want me to start at instead of like doing this but skipping the first, I don't know, like, you know what I'm saying? So like in practice, no, there's no reason that would really ever happen. Okay. All right. So summation formulas. What we're going to be doing in 5.2 to actually find these integrals is akin to when we use the limit definition of a derivative to calculate the derivative, right? There's no shortcut. So in order to do these integrals, we're going to convert them into these infinite sums. And to evaluate those sums, we're going to be using these summation formulas. Okay? So this is not something I expect you to memorize. The AP would not expect you to memorize these things, but you will use them repeatedly in the homework today and then never again. Okay? Pierce.
Are they like add a question where you need to use it? We'll say like use this equation.
No, it will not. So there are these 3 that are your 3, like, this is not intuitive at all. Maybe the first one is, but even after, certainly the second 2 are not intuitive at all.
The first one, squared.
I mean, it would be n squared plus n over 2. So, yeah, I'm not going to derive it for you. It's an easy derivation, but and then we have these other 4, and now these are kind of minor ones. They're really to help you like rearrange your sum so you can get to the point where you can use those first 3. So the first one says the sum of a constant is just n times the constant. So if I add up 7 12 times, I get 7 times 12, right? That's all that's really saying. If I have a constant time, or the sum of a constant times a function, I can pull that constant out to the front, right? If I have like 7 times 3 plus 7 times 4 plus 7 times 5 plus 7 times 6, I can pull the 7 out and just do 7 times 3 plus 4 plus 5 plus 6. That's all the second one is saying. And the last 2 just says you can distribute your sum across addition and subtraction, which should make sense, right? If I add up like 1 plus 2, and then 2 plus 3, and then 3 plus 4, that's the same thing as adding 1 plus 2 plus 3, and then 2 plus 3 plus 4. And then adding those 2 sums together. Okay. Let's do an example of now how we have to do some rearranging and how we're going to use those summation formulas to do some actual problems. Okay. So part A says evaluate the Riemann sum for f of x equals x cubed minus 6x, taking the sample points to be right endpoints, a to be 0, b to be 3, and n to be 6. So my Riemann sum, again, is going to be the summation, right? So I'm going to calculate the delta x, which is b minus a over n. In this problem, that's 3 minus 0 over 6. So 1/2. And I'm going to calculate xi, which is a plus I delta x, which is 0 plus I times 1/2, or I over 2. So far, so good. So for me, we have our sum from I equals 1, and again, our n is 6 of f of I over 2 times 1/2. Is everybody okay with how I've plugged that into the calculator? Or plugged this into the equation? Is that okay? Now, rather than doing this addition by hand, I am going to ask my calculator to do this for me. Perfect, right? Particularly on the AP exam, if you have a calculator active question and you're asked to do a Riemann sum like this, I don't want to waste 2 or 3 or 4 minutes by like having to write out 5 or 6 or 10 or 20 multiplication problems and type them into my calculator and add them all up. I want to just do it in one fell swoop. The calculator can do this for us. I invite you to take your graphing calculator out so you can follow along with me. I'm going to begin by pressing the y equals button, and I'm going to clear out anything that happened to be in my y equals menu and type in the function for this problem, the f of x, which was x cubed minus 6x. I'm going to pause for a minute here and check my mode and make sure I'm in radian mode. I don't know exactly the programming that it's going to use to do the calculation that I'm about to do. But if it needed to be in radian mode, if it needed a specific mode, it would be radian. So I'm just going to check that. For AP Calc, it should always be in radian mode. I teach a bunch of classes, so I switch it on all the time. And so I have to just, probably once a day, I'm in the wrong mode and I catch myself there. All right. So what I'm going to do is I'm going to do the 1/2. That's my delta x. Right? So this part can just kind of come out to the front, which is what I'm going to do. And now I'm going to do this sum. So I'm going to press the math button, and I'm going to scroll down until I see the summation command. There it is, option 0. And I'll press enter. And that gives me the summation symbol on my calculator. So now I'm just going to type it in the way it looks, except instead of using I, I'm just going to use x. So x equals 1 to 6. And then I typed my f of x into y1. So I'm going to go retrieve that. I'm going to press vars over to y vars, function y1 of x over 2. So I pressed vars, which is right underneath the down arrow. I moved over to the y vars tab, selected function, and then y1 is the first option. Of x over 2, right? Because ours is I over 2. And then I press enter, and that's my number. It added up all those rectangles for me, and I just get a number. How beautiful is that? That's negative 3.9375. I did vars, which is below the down arrow, over to y vars tab, function y1. Does that feel okay? What a time saver that is, right? Feel free to use that on a test. Like if you show me the sum that you've set up, I do not need to see the work on how you did it after that. You can always do it by the long way. That's okay. If there's only 6 rectangles, that's not so bad. You could do it. It's kind of stinky, but like you'd survive. But certainly you could do it this way. Pierce.
I got 800.
What is in your y1? Is it x cubed minus 6x? Uh,
1/2 plus.
well, it should be times.
Oh, time.
That's times?
Oh. Yeah.
I invite you to sit as close as you'd like to the board.
But I.
That's as big as I can make the calculator.
That is fine. I didn't hear times.
Chanel?
So, you're pretty much like taking this equation, making it into like an integral equation, if that makes sense. Like what you did, or did they already give it to you, the integral equation?
I'm doing part A, so it's asking me to do a Riemann sum with 6 subintervals.
Okay, so 6, yeah, so you did 3, okay. And then this equation over here, how did you know to use the xi equation? The xi equal a plus I times change of x?
Because I have an xi in my formula.
Okay, I'm so sorry, what does that formula represent again? Xi equal a plus?
That's the Riemann sum formula.
Oh, okay, so if you're doing a Riemann sum, you have to use that formula?
Yeah. Right? Like if we go back here,
Oh. Okay,
those are the formulas you'll use every time you use a right end.
I'm sorry about that.
That's okay. Pierce, what's up?
You think you'd be able to help me right now?
Can we get it in a minute? Okay. All right. So part B now is we've got an approximation, right? Part B is we're going to find the actual exact value now. So the integral from 0 to 3, and I'm just going to write f of x dx here. No, I'm not. I'm going to write it out. I lied. So I need to convert this into the limit of n goes to infinity of the sum I equals 1 to n of our function with xi plugged into it times delta x, right? Now I know delta x is equal to b minus a over n, and xi is equal to a plus delta x times I. Does everybody feel okay there?
Did you put in 0? Is it in, oh,
A is 0. So I have the limit as n goes to infinity, the sum from I equals 1 to n. And now in place of xi, I'm going to write 3I over n cubed minus 6. And instead of xi, I'm going to write 3I over n. And then I'm going to write my delta x, 3 over n. Is everybody okay with what I've written here? Braden? Okay. So now what I'm going to do is I'm going to simplify here, and I'm going to pull this out in front of my sum. Actually, we're going to write it this way. So 3I over n squared is 27I cubed over n cubed. And I have minus 18I over n. Yes, because the limit is applying to all of that stuff, right? So there's like a time symbol in between the sum and that 3n. I'm now going to distribute my sum across that subtraction. Oops.
Is that from one of the rules from there?
Mm-hmm.
Okay.
And now I'm going to distribute the 3 over n to each sum. And I'm going to pull the constants from the sum out to the front. So I'm going to do 2 things on this step. So I'm going to have 3 over n, and then I'm going to have 27 n cubed, and the sum I equals 1 to n of I cubed, minus, and I'm going to have my 3 over n, and then 18 over n, sum I equals 1 to n of I, because I've just gone and did that. And then I took the stuff without an I and moved it out front. Does that feel okay?
You just did 3 over n times that integral?
There's no integral. You sum, I think is what you mean.
Yeah. I'm sorry.
That's okay. So I distributed the 3 over n to each sum. And then inside of each sum, I pulled the constants to the front. Right? So now I recognize that this is one of those formulas that we gave just a moment ago. If I scroll back up, it is, where did they go? There it is. And the other sum is this one here. So I'm going to drop those in place of the sums. Talika. Absolutely. You're going to miss the best part, though.
Oh, no.
I know. It's okay. When you got to go, you got to go. All right. So out front, I'm going to combine my like terms. And then in place of I cubed, I wrote n plus, or n times n plus 1 over 2 squared. I'll combine my like terms. And in place of I, I'm going to write n times n plus 1 over 2. Is everybody okay with what I did there? Now let's look here. If I look at this, let me pick a different, well, let me erase that. Okay. If I look at this, I'm doing the limit of this, right? If I look, the numerator is a polynomial, a degree 4 polynomial. N times n plus 1 is degree 2, but it's squared, so it's degree 4, with leading coefficient 81. The denominator is a degree 4 polynomial with leading coefficient 2. So that first limit turns out to be 81 over 2. Let's look at the second limit now. The numerator in the second limit is a degree 2 polynomial, n times n plus 1, with leading coefficient 54. The denominator is a, that should be 81 over 4. Why is it over 4? 2 squared.
Oh, that's a good catch.
Yeah, I would have missed it. Almost missed it. All right. The second limit is a degree 2 polynomial with leading coefficient 54 over a degree 2 polynomial with leading coefficient 2. And we'll just make a common denominator here and subtract, and I get, what's that, negative 23 over 4, which is like, is that not right? 27, thank you. Yeah. So it's negative 6.75 is our actual answer.
That's crazy.
Okay? Now, this is the process you're going to use to find integrals in this chapter or in this section. Negative 27 over 4.
No, 81 minus 1.
Oh, it should be 108. That's why. Goodness gracious. 54 times 2 is 104, right?
Yeah.
Obviously, every time. So, again, when you're doing your integrals in this section, this is the process you're going to be doing. And this stinks, and we're going to get rid of it in the next section. But I think it's important that you see that, in theory, this is how you have to do this. Okay? All right, let's do another. So part A says, set up the expression, the integral from 1 to 3 of e to the x dx as a limit of sums. And then it says, use a computer algebra system to evaluate this. None of us have one of those, so we're just going to skip that part. We'll just do the setup. Oops, dx. So that's the limit as n goes to infinity of the sum I equals 1 to n of f of x I dx, or delta x. Everybody's okay? All right. So our delta x is 3 minus 1 over n. Our xi is 1 plus 2 over n times I, or just 1 plus 2i over n. So our sum here then, the limit as n approaches infinity, sum from 1 to n of, if I plug this in for the x in my f of x, I have e to the 1 plus 2i over n times my delta x, which is 2 over n. Done. Okay? You don't have to do any more because it says do not set up. I'm done. It's ready to be plugged into a calculator. If you had a calculator that could do it, I don't think anybody does, so we're stopping here. I checked to see if I still had the operating system for a computer algebra system on mine. I don't anymore. I don't know what happened to it, but I have a good calculator at home that can do it. And I have one here that has no batteries in it.
Wait, how many calculators do you own?
A lot. Okay, so here it says evaluate the following integrals by interpreting each in terms of areas. So remember that the integral is the area under the curve, right?
Yeah.
So if this graph is just like a geometric figure, I can just use my knowledge about area from geometry to compute this integral. So let's look at the graph of square root of 1 minus x squared from 0 to 1. So I'll go to my y equals 1 minus x squared, and I'll change my window from 0 to 1. And we were probably set at negative 10 to 10 before, so I'm just going to leave it set there. And I'm going to add graph. See what I got. Well, I got a lot of extra up and downs, right? Can't really tell what this looks like. But it looks like everything happening between 0 and 1 on my y. So I'm going to change my y min to be 0 and my y max to be 1. And try again. What does that look like to you? How much of a circle? 1/4. I agree. So pi r squared is the area for a circle. What's the radius for this circle? 1. And we're done. We just have pi over 4.
Could you show me how you graph it?
Yeah.
So I just typed it into y1, And the window I used was 0 to 1 and then 0 to 1.
Square root of 1 minus x squared.
Yep. Nothing fancy. Let's do the next one. So I'll do x minus 1. I'm going to change my x min to 0 and my x max to 3. And I'm going to reset my y's to negative 10 to 10. And take a look at what I got. Straight line. It looks like we go from negative 1 to 2 probably, it looks like. So I'm going to reset my y's from negative 1 to 2. So when I look at this, what I see is one triangle here plus another triangle here.
So I don't even know what how to zoom in. Like, how do you know like to zoom into that like negative 1, 2 for the
Because
y?
I counted on the y's before as to where they looked like where the lowest y and highest y was. I just counted the tick marks on my y-axis.
What do you did you just like see which one made a picture? Like
So I started at negative 10 to 10, right? Because that's just kind of what the standard window is. And I literally looked here. That's the lowest y, looks like at negative 1. That's the highest y, looks like at 2. So I just literally just read the scales and went from negative 1 to 2. Oops. Yep, I got it. Okay. Now what's the one thing I have to be careful about here with my two triangles?
One's negative.
What first triangle is negative? Yes.
wait, what?
Why is the first triangle negative?
It's like below the x-axis.
It's below the x-axis. Perfect. Very good. What's the base and height for that first triangle? Base is 1, height is 1, right? We're taking care of the negative already. I wrote it out front already, so you don't have to worry about it there. And if I look at the second triangle, the base is and the height is, okay? And we're done, right? Oops, that should be 1/2. Everybody happy there? Almost guaranteed there will be an AP exam question at some point, either multiple choice or free response, where you're given like some goofy looking curve they're asked to find the integral of, that you just chunk up into geometric areas and add them all up. Almost guaranteed. You'll see that at some point. Classic AP exam question. Perfect for a no calculator. Because if they do a piecewise graph, everything can be a whole number, and it'll be pretty easy. All right. So remember, we had done left endpoints and right endpoints for our rectangles. Here it's giving us a formula if you want to do midpoints. So the only difference here is just the way we calculate our xi's, as it's the midpoint of xi minus 1 and xi. The middle value between those. So for this, again, we're going to use the limit as n it's a Riemann. So my area is approximately the sum from I equals 1 to 5. And then my delta x should be 2 minus 1 over 5. And my xi bar should be 1/2 xi minus xi minus 1. So remember, our formula for xi from before is a plus delta x times I, and then we're going to minus a plus delta x times I minus 1. Everybody's okay there? When I do that, I get The 1's cancel out. I get 2i over 5 minus 1/5. Everybody's okay? Because I distribute that through. So I'm going to have f of 2i over 5 minus 1/5 times 1/5. And now it's calculator time. Braden. Oh, thank you. So make those over 10. Thanks. Perfect. And yeah, I know I could reduce the 1, but I don't care. Because it's all going to my calculator anyways, right? So for y1, I'm going to put in 1 over x. And then I'm going to have my delta x times, and then math. Go down and pick the summation command. That's command 0 on my calculator. And in place of I, I'm going to use x's. So I equals 1 to 5 of, and instead of f, we're using y1. So vars, y-vars, function y1 of 2x over 10 minus 1/10. And there we go. Everybody okay? The only difference is the way you calculated your xi, right? That's the only difference in the midpoint formula. Yes, Chanel.
Where'd you get the 2i over 10 minus 1 from? I missed the formula.
I just simplified that.
Oh, is that from the?
That's this, which is just the xi formula from before. Okay, properties of these definite integrals. The first property is if I swap the bounds. Notice this one is going from B to A and this one goes from A to B. All that happens is that the sign of the area switches. Goes from positive to negative or negative to positive. Whatever. Easy, right? If I integrate from A to A, what's the width of that rectangle going to be? 0. What's the area under the curve got to be? 0. That's fine. Additional properties. So if I integrate a constant, that's just a straight horizontal line. So that's going to be, if I do the area under that curve, that's just a rectangle. The height of the curve is just C. And the base of that rectangle is going to just be B minus A. So that's all that is a rectangle. 2 and 3, just like my summations can distribute across addition and subtraction, integration can distribute across addition and subtraction, because all it really is a sum. So it should have the same formula or same property. And just like our summations, if I have a constant inside my integral, I can pull it out front. Just like my summations, because an integral is really just a sum. Does that feel okay? Okay. All right. So it says here, use our properties of integrals to evaluate this. So I would start by distributing my integral. Everybody's good there? This first piece I can use property 1 on. That integral is done because it's just the integral of a constant. The second piece, I'm going to pull out that constant of 3. And now this I have to do the long route and convert that into the limit of a Riemann sum. So I have 4 plus 3 limit as n goes to infinity, sum I equals 1 to n of xi squared delta x. Our xi in this case is going to, or our delta x in this case, got to do that first, is 1 minus 0 over n, or 1 over n. Our xi in this case is a plus delta x times I, or I over n. So this is going to be 4 plus 3 times the limit as n goes to infinity of the sum from I equals 1 to n of I over n, quantity squared, times 1 over n. I'm going to pull all the constants out front of my sum, so I can take out a 1 over n cubed. Did you guys see why it's cubed? Okay. This is now one of my formulas. So if you go back and we look, that is n times n plus 1 times 2n plus 1 all over 6. I notice that limit is a degree 3 polynomial on top with a leading coefficient of 2 over a degree 3 polynomial with leading coefficient of 6. So the limit is 2 over 6, or 1/3 if you prefer. Three times 1/3 is 1. 4 plus 1 is 5. Chanel.
Oh, I'm so sorry. For the previous question, I said a quick question on it. I know it works like that.
The previous question,
Yeah.
this thing from way back here.
Yeah, that one.
Okay.
Where'd you get the 1 from? For 1 plus 1 over 5i.
The value for a is 1.
Oh, okay, got it.
It's the lower bound on my integral.
Got it.
Okay. Next property of integration. This should be very straightforward because we've used it already intuitively. Hi, Carrie.
Thank you.
You're welcome.
Even now.
You knew it. All this property is saying is I can break up my integral along its limits of integration. So remember when we did, I don't think maybe you need it at the front desk, I don't know. Remember when we did this just a moment ago and we broke that integral problem into 2 triangles? We broke this into the integral from 0 to 1 plus the integral from 1 to 2. That's all this property here is saying, is that you can do that whenever you want, right? If you go from A to C and then C to B, that's the same thing as just going from A to B. So you can break them up or combine them together, whichever way you want to go. That's something you can do as long as the upper bound of one matches the lower bound of the next. Together they go. Everybody feel okay? All right. So let's take a look at this problem. It is known that the integral from 0 to 10 of f of x dx is 17. The integral from 0 to 8 of f of x dx is 12. And we're asked to find the integral from 8 to 10 of f of x dx. So what I notice is the upper bound of this one matches the lower bound of that one. So I can say the limit, or the integral from 0 to 8 of f of x dx plus the integral from 8 to 10 of f of x dx equals the integral from 0 to 10 of f of x dx. Everybody's okay with that? I'm told that this value is 12 and this value is 17. What does that value have to be then? 5. 12 plus 5 is 17. And we're done. Easy enough? Does that feel okay?
Yes.
Very easy concept to apply. Our last set of ideas are these comparison properties, which are very intuitive. So if our function is positive over the entire interval, the integral is positive over the entire interval. Well, of course, because the heights of all our triangles are positive, right? Or rectangles, I should say. If f of x is on top of g of x, right? So f of x is here and g of x is like here. If I integrate those over the same interval, the integral of f of x has to be bigger than the integral of g of x. Well, of course it does, right? There's more area under f of x than there is g of x. So if m is a lower bound for f of x, so if this is like f of x and m is here and cap m is here, an upper bound, if I look at the rectangle formed by the lower bound and the rectangle formed by the upper bound, the integral of f of x has to be between those two values. That's what the third piece is saying. So our last example here, right? Yeah, good. Is saying use property 8 to estimate the value of integral from 0 to 1 of e to the negative x squared. So what I'm going to do is I'm just going to graph that e to the negative x squared on my calculator. And I'm going to graph it over 0 to 1. And I'm just going to look for a lower bound and upper bound for that function. Cool. Looks like it's decreasing the whole time, right? So cap m should be f of 0, and little m should be f of 1. Everybody's okay there? So this is 1, and this is e to the negative 1. Okay? So I know that little m times b minus a has to be less than or equal to the integral from a to b of f of x dx, which has to be less than or equal to cap m b minus a. So little m was e to the negative 1, b is 1, a is 0. Cap m is 1, b is 1, a is 0. So somewhere that integral is between e to the negative 1 and 1. And we're done. So the homework quiz for next time will be based on homeworks. These homework problems I've bolded there would be the ones in particular that I'd want to make sure that I've looked at and I tried to do. How did this feel today? Was okay, I hope. Again, it's a little messy right now. The next chapter or the next section, we get away from having to do these summation formulas. That goes bye-bye, at least until you do anything theoretical or whatever. But like, gone, done, no more, which is cool. I'm good with that. And we learn how to do integration with some shortcuts. And as we go through, we're going to keep learning new integration shortcuts and how to do more and more difficult integration problems. But I want to say one thing about this. We talked when we did derivatives and talking about like, hey, you could do some algebra at the start of this to make this derivative easier. It is even more important on integration to look for algebra at the start to make the integration something you are capable of doing at this level. Okay? I can give you something where without simplifying, it's impossible for you to do with the tools you have available to you. But after simplifying, we can do. And we're going to look at all kinds of interesting simplifying tricks that we can do beforehand to make the problem doable. And we're going to see, 3, 4, 5 sets of tricks on how to deal with like, oh, what if I have something that looks like this? I don't know what to do with this. Okay, here's what you do. And we're going to do this over and over and over throughout the semester. Okay? In addition to looking at applications of like how we can use integration to solve like real world kind of problems. But also we're going to look at like just the tricks on how to do integration, period. Is everybody cool with that? We did it. All right. Everybody good? I'm going to stop. All right.